So in the last lecture, we were looking at the changes that an operator can do to a generator to basically operate it in different modes. We looked at three different kind of modes. One is where the excitation current is increased, and that impacts on the voltage E0, and is causing the voltage E0, the magnitude of that voltage, to exceed the infinite burst voltage, which is E, and that operates the generator in the mode of delivering reactive power into the system, right? So it's basically exporting reactive power by basically over exciting the electrical generator. And the second mode that we looked at last week was under excitation, where now the operator basically reduces the excitation current such that the magnitude of the phasor E0 is lower than that of the terminal voltage or the utility voltage, and hence what happens now during under excitation, the generator is absorbing reactive power Q from the system into the machine. So this is those two types of operation doesn't involve any exchange of active power. So in the last section we looked at how the active power can be transmitted from the machine to the utility by basically applying more steam on the turbine or more flow rate of water on a hydro turbine, and that will basically shift the phasor of the E0 and at a certain angle with respect to the terminal voltage, right? And hence you will get this angle that we discussed, which is angle delta. And this angle is what determines how much active power is going to flow from the generator into the utility grid, right? So and the current that's basically in the stator, which is I, is due to this angle delta, right? So in this operation, the machine exports active power into the system, and hence we basically fulfilling the main objective actually of the generation system, where we exporting active power into the system. Normally we don't operate the generator in the other two modes because the consumption of reactive power, we expect the consumers to basically generate their own reactive power, and it's not basically being transmitted by the utility. So today we will go into more detail into the physical interpretation of the synchronous generator behavior. So we will look at how this mechanical torque that's being applied to the machine, how does that interact with the electrical torque, and hence we basically convert this mechanical energy into electrical energy. Right. So if we go back to the basics, as we know that the three-phase currents flowing in the stator of a machine, same as in your induction machine, it produces a rotating magnetic field, right? So the speed of this rotating magnetic field is basically your synchronous frequency, right? And in a synchronous generator, the rotating magnetic field, right, it rotates at the same speed and direction with the rotor, right? So as opposed to your induction machine where the rotor needs a certain speed difference between its speed and the synchronous speed so that you get a slip, and hence you have induction that happens. For the case of synchronous generators, we don't have that slip. They basically rotate at the same speed and same direction, right? So obviously, the respective fields produced by the rotor and the stator will basically be appearing to be stationary with respect to each other because they are rotating at the same speed. And also the stator will have the same number, right? So now depending on this different position between the stator and the rotor, we have basically very powerful forces of attraction or repulsion that may set up between them, right? We will start with the first figure here, which is figure 18. And here, basically, we will start at the very beginning where you're synchronizing the generator with the utility. So if you remember from the steps that we've discussed for synchronization, the very first step we do is we make sure that the generator is floating on the line, meaning that the two phases E0 and E, they're basically lying on top of each other, right? So for that to happen, it means that there is no current flowing in the stator winding, right? So you're only applying a certain field current, which is Ix on your rotor side, and you're generating an induced voltage E0 that's basically equal magnitude with that of the terminal voltage of your system, right? So when the generator floats on the line, there is no angle difference between the two phases, E0 and E, and hence your stator current is zero, right? And hence there are no forces developed between the rotor and the stator. So that's your rotor and that's your stator. As you can see, the currents in the slots on the stator, the conductors are now not carrying any current. So it's only the rotor that's carrying the current Ix between those two sides of your field winding, and it's producing a certain flux phi that's passing through the gap. But when the generator floats on the line, there is no current induced on the stator side. Now, when the operator of the plant starts to basically apply mechanical torque by admitting more steam, for example, on your steam turbine, basically what happens is the rotor will start to advance, okay, at a certain angle with respect to the axis of this rotor, or with this rotor axis, okay. So this is what we will see in the next figure. That's figure 19, right? So now when the operator starts to apply more steam, because you can see that now the rotor has advanced at a slight angle with respect to the initial axis, okay? So we have what we call a certain mechanical angle alpha that's being basically introduced between the axis of the rotor and the axis of the stator pole and the axis of the rotor pole, right? So there's a certain angle alpha, and as we've discussed, you can use a certain equation to basically convert alpha to delta, right? So delta is equal to alpha times P over 2, and you'll get the electrical angle delta, which you're more familiar with. And the moment there is a certain angle delta, as we've discussed, now current will start to be introduced on the rotor side. Okay, so now you will see that are being induced in the stator windings, right? And from your Faraday's law, you know that the way currents are induced, it will try to flow in such a way that it opposes the change that's causing the current to be induced, right? So now, as you can see, the mechanical torque is pushing the rotor forward, right? It's advancing the rotor with respect to the axis of the stator pole, and hence the currents now, they are induced in such a way that if this is a north side, they will basically induce the current will induce in such a way that now you will have a south side on this side, such that now you can see the field lines are pulling the rotor backward, trying to basically reduce that angle back to zero, right? So that's the effect of Faraday's law to oppose the change that's causing the induction of current. And so basically this force of attraction that's pulling the rotor back, so is basically what you call your electrical torque, and it basically acts in opposite direction with the mechanical torque, right? So the mechanical torque in this case is basically clockwise, and as you can see now, if this is clockwise, the electrical torque is anti-clockwise, right? So it's going to oppose the mechanical torque. So that's basically how the electrical torque is induced on the rotor, and hence for the machine to convert that mechanical power to electrical power, obviously work has to be done. So you need to basically oppose that electrical torque, and hence you basically convert the energy from mechanical to electrical. Now, if you go to the next slide, as I said, this equation 6 here is basically showing you how you can convert the mechanical degree into electrical degrees, which is the angle that you require for your phasor diagram, right? So the relationship is basically the torque angle is given by the product of the number of poles on the generator times the mechanical angle in degrees divided by 2, and you will get the electrical, the angle, load angle delta. Right, so in this section, we were basically just showing you how electrical torque is counteracting the mechanical torque for the generator to basically do work and hence convert the energy from mechanical to electrical. So now moving on to the next section, we will basically now show how you can calculate this electrical power that's being produced by the generator. So if you look at section 19, it's basically presenting equation 7, right? And equation 7 is basically an equation that you will use quite a lot in this first chapter of the generator, synchronous generator. It's basically the equation that's giving you the active power per phase for a synchronous generator. So from your phase diagram, as you can see, you know what is the magnitude of the induced voltage, of the terminal voltage. That's the load angle or the torque angle, right? So that's the angle between those two phases, E0 and E, and that's your synchronous reactance. So if you know all these parameters, you can basically compute the active power that's being produced by the generator per phase. So that's for one phase. And if you want the total power, you multiply by 3 here, right? Then you will get the 3-phase power that's being produced by the synchronous generator. Now, if you look at figure 20, as you can see, it's basically plotting the active power per phase versus the torque angle. Okay, so in this case, we're assuming that obviously we're not changing the field current, so Ix is kept constant, and hence E naught is kept constant. So if these parameters are constant, E naught and the synchronous reactance, and we vary only the angle delta, basically you end up with the sinusoidal curve that's basically representing the active power versus the torque angle, right? So you will see that initially you have a linear increase in the power when you increase the torque angle delta, and obviously you reach a maximum power when your angle is at 90 degrees. So what happens is the sine of delta is 1, and hence the maximum power is given by this equation here, which is E naught times E divided by XS. So basically substituting sine of delta to be 1. All right. So normally, when you operate in this region, which is from 0 to 30 degrees, right? So your power is expected to increase almost linearly. And as you reach 90, obviously, then the maximum power is reached, where sine of delta is 1, and you can compute the maximum power. This is the maximum power per phase. And if you multiply by 3, you will get the maximum 3-phase power. Right. So if you exceed this power, right, if you keep on increasing delta, what will happen is the generator will lose synchronism with the infinite bus, and hence what will happen is it will trigger your protection system to trip the generator off the grid. Right. So normally we do not approach this angle. We try and operate it in the linear region in most cases, right? Now, when it comes to the control of this power now, so this is basically covered in section 20, right? So the speed of the rotor in a synchronous generator is basically directly related to the frequency of the output voltage of the machine, right? So that we looked at that in the very first equation 1 that we showed earlier in the first lecture. And the speed of the rotor basically is a measure of the frequency of the generator. So if you want to keep the synchronous generator synchronized to the system, as we discussed earlier, one of the main factor is we have to basically have the frequency of the output voltage of the generator to be equal to the frequency of the infinite bus system. Okay, so those two frequencies must match, then basically your generator is synchronized with the infinite bus. So if you look at generating plants, basically they are equipped with a certain control system to keep the generator obviously synchronized with the infinite bus. And how they do that is they use what we call a load frequency control system. And the main component of that load frequency control loop is basically your governor system. And the governor, what it does is basically it measures the speed of the generator and compares it with the required speed, which is basically to keep your frequency to be constant. So you obviously then you need to have a certain fixed frequency speed that you need to match. So the control loop basically tries to match that speed, the reference speed, with the actual speed of the machine, right? And it detects changes that basically are as small as 0.01%, right? So in case there is, for example, an increase in the load, right? So what happens is you will find that the generator will have to basically match that increase in load. And for it to happen, firstly, that the frequency of the system will drop. And if the frequency drops, what happens is this load frequency control loop will basically detect that change in frequency, and basically then will effect in modifying the valve or the gate opening of the turbine such that the load on the generator is matched with the mechanical power on the system, right? And hence basically restore the frequency of the entire system. Right, so this is for the first part, which is on the controls around the synchronous to an infinite bus. In the next section, we will basically look at the transient on the synchronous generator, transient conditions. So this section is covering a small, we're introducing what we call transient reactance in this section. It's very introductory. We won't go in very detail in this section because in machines 3, we look at this section in more detail, and we will basically go more in detail in machines 3. So for machines 2, we will just introduce the basic concept of this transient reactance. So if you look at a generator that's connected to a infinite bus, there are many contingencies that may happen in the system. One of them is load changes, right? And for example, you may have a sudden increase in the load, and now this model of the generator that we have used so far basically is derived for steady state operation. So when we use this model where we have E naught as basically a source and we have your synchronous reactance in series with that, this equivalent circuit is only valid when you have a steady state operation of the synchronous generator. Now, if you have this kind of environment where suddenly your load changes, or for example, you may have a sudden fault on the system, so now what happens is the equivalent circuit that we've derived so far will not reflect the behavior of the machine. Okay, so in this case, what we do is we have to modify the equivalent circuit to basically represent this transient operation of the generator. And how we do that is we replace this reactance, which is originally was XS, into a reactance that is time variant. Okay, so we're calling it the transient reactance, and basically it's a reactance that varies as a function of time, right? So this is an example where in figure 21 we're showing effect of basically applying a short circuit at the terminal of a generator, right? So what happens is initially the generator was operating at steady state, right, and it was delivering, for example, its load current, and suddenly when you apply the short circuit, as you can see, the reactance, armature reactance of the generator changes its value from XS to X-D, which is called the transient reactance, and then it gradually increases back to XS at steady state after a certain time cycle, right, which is T. Now, this value of T depends on the generator parameters, and it basically determines how long does the reactance. Basically, you can see it's the first order response increases back to its original value of xs. Now, this we will, when we go into machine 3, then this curve will get a little more complex. But in this machines 2, we keep it in a simple form where we're showing only the transient reactance in this case of a short circuit. Now, obviously, you can see that the synchronous reactance has dropped its value when you apply a short circuit. When the synchronous reactance changes to a smaller value, the way it's basically helping the system is that your drop across the synchronous reactance is not too much, because now the reactance has dropped, and hence it's helping in terms of voltage variation when there is a certain sudden load increase in the generator. Okay, so it helps to lower the voltage drop across the synchronous reactance. Okay, so that was for the transient response of a synchronous generator subjected to a sudden disturbance. Right, so I will, in the next section, we will look at section 22, where we're looking at the power exchange between two areas in a power system, right? And we will look at how we can transmit power from one region, which is region A, to another region, which is region B, right? And how we can draw the phasor diagram between the two regions, right? So this equivalent circuit is representing two load centers and an intertie, which is a transmission line between two areas in the power system, right? So if you look at that figure, the phasor diagram of figure 22A, so let's look at this phasor diagram here. So as I said, we have basically a certain magnitude here. For region A, the magnitude of the voltage is given by E1, and the magnitude of the voltage for region B is given by E2, right? And we can see that the transmission line is basically carrying a certain current I, and it has a certain reactance. The transmission reactance is X, and basically from this equivalent circuit, you can basically determine the voltage E1 is equal to the drop across the transmission line plus the voltage E2, right? So this is writing the voltage across the line and the voltage across the second region B. Now, if we look at the phase diagram, we can see that we made an assumption here that we have a lagging current flowing in the transmission line, and this current lags the voltage E2 by a certain angle theta, which is based on the power factor of the system. And then basically what happens is we are assuming also that E1 leads E2 by a certain angle delta, right? So that's basically showing you this diagram here. So E1 is leading phasor E2 by a certain angle delta, and I has a certain angle theta with respect to E2, which is due to the power factor on this side here, right? So by solving cos theta is equal to the power factor, you can determine the angle theta, right? So obviously for you to now determine the voltage E1, right? So the voltage E1 here is the sum of this phasor, right, time plus the voltage across the transmission line. So it's the in vector form, and adding the drop across the line, you basically get the voltage E1. That's the phasor sum of those two voltage. I times X I times X plus E2. Right, so basically the active power that basically now will be absorbed by region E2 is given by this equation A. So that's the product of E2, the sum, so that's the magnitude of the voltage in region B times the current that's basically passing through the source there, and that's the power factor on the receiving end, right? So now if you're applying sine rule to this phasor diagram here, basically you can write this equation here. So I times X over sine delta will be equal to E1 over sine phi, and that can be also equal to E1 divided by sine of theta plus 90, right? So if you look at this figure here, we're basically telling you that this is delta, right? So, and this is phi. So E1, okay, is subtended by this angle phi, right? And sine of delta will be subtended by this part, right? So this phasor is subtending this angle delta, and this angle here, right, will be basically the next part, that's E2, which we didn't show on this sine rule. Now going back to solving this equation, so I times X over sine delta is equal to E1 over cos theta, and we can basically write I cos theta to be equal to I1 sine delta of X, right? And we can substitute this equation back to equation A we saw earlier, which is this one, right? So we replace I sine theta, and we end up with E times E1 sine delta of X there, right? So what it's telling you is the power that's transmitted between region 1 to region 2 is given by the product of the magnitude of the two voltages on each end times the sine of the angle between those two voltages, and divided by the transmission line reactance. Okay, so you can see that this equation resembles that of the generator power in the system. If you look at generator, you have two voltages. You have E naught and E, and sine delta over XS. So it's an easy way to remember that for a power transfer between two regions, it has the same format. It's just now you're going to use the voltage from the sending end to the receiving end, and the angle between those two voltages. All right. So the active power that's received by region B is equal to the power delivered by region A. Again, just remember that in this model, we're only modeling the inductance of the line. We didn't model the resistance. Obviously, then there is no losses, and that's why we can equate these two powers. So power delivered by E region A is equal to the power received by region B, as this is a purely inductive line and the line is not consuming any active power, right? So in the next slide, I will basically present how we can generate the capability curve of a synchronous generator. Right, so if we look at a synchronous generator, the operating characteristic of the machine is described by the interrelationship between those parameters: the terminal voltage, the field current, armature current, the power factor, and the efficiency. Okay, so the real power basically is determined by, as I said, the amount of the angle, which is basically the angle delta, and the terminal voltage basically is normally fixed by the infinite bus. Now, if basically these two parameters are fixed, okay, your maximum reactive power that the machine can deliver is limited by, obviously, your either the armature or the field winding heating, right? So we will look at the first case where we will push the generator to operate at maximum armature current, right? So basically we'll operate the generator to deliver a current of 1 per unit, which is the rated current, and we will fix the terminal voltage also at 1 per unit, which is its maximum value. And by basically operating the generator in this mode, it will correspond to an apparent power that's basically being determined by the product of the terminal voltage times the current, right? So E times I will basically give you S, which is the apparent power, and that's basically the square root of P squared plus Q squared, where P is your real power and Q is your reactive power. So this equation basically is giving you the equation of a circle. Obviously, the radius of the circle is basically E times I, right? Where E is your vertical axis and Q is the horizontal axis. And this is what I've shown here in the next slide. So you can see, P is on your horizontal axis and Q is on the vertical axis, right? So we're generating this first circle here, which is basically called the armature heating limit. So if you exceed this current, obviously you will fall outside this region, and hence your armature will overheat. Okay, if you exceed the rated current of the armature. Right, so let's go back to the second slide. If we basically now, instead of focusing on the armature heating, if we now want to basically look at how much reactive power can the generator basically produce, right? So if you operate the machine on the constant terminal voltage, okay, and now you limit the field current Ix to its maximum value, that what will happen is we will basically now determine how much of reactive power can the machine basically deliver. So if you look at the phasor diagram that I will show in the next slide, right? So if you look at this phase diagram, this is your equivalent circuit of the generator. And so you have E naught induced voltage, that's your synchronous reactance, that's I, and that's E. So this is the phasor diagram of this particular generator when you have a certain lagging power factor load basically connected to the terminals of the generator. And if you basically if we try and resolve those phases, as you can see, this is the phasor Ex, which is the product of I times Jxs. Hence, what happens is the this angle here will be your angle theta. So you end up with two components here, right? So if you see these two phases, one is basically your vertical, and that's your horizontal, right? So if you are resolving with respect to angle delta, so this will be IA times XS, and this one will be IR times XS, right? So another way you can basically determine this is by resolving E naught with respect to delta, right? So if you resolve even E naught basically vertically with respect to delta, you will get E naught for this part is E naught sine delta. And if you want this small part here, right, so you will take E naught basically cos delta, that will give you the whole part here up to here. That's E naught cos delta. And if you subtract E, which is this part here from here to here, then you will get only this part. So that's E naught cos delta minus E. So this is what I've basically written here. So I said that IA times XS is equal to E naught sine delta, and IR times XS is equal to E cos delta minus E, right? And basically this is the two equations that I've written there, equation 10 and 11, right? So I'm basically calling I cos theta to be the IA. So the A stands for the active component, active power, and I sine theta, I called it R. So that's for the reactive component, which is reactive current, right? So as you can see, we can derive those two equations, IA and IR. And if we multiply the active and reactive components of the currents by E, which is the terminal voltage, we end up with P and Q, right? So P is IA times E, and Q is IR times E. And we can also use equation 10 and 11 and write them in terms of delta. Okay, so that will basically produce equation 12 and 13. Right, so in this derivation, I'm basically showing you how if you take P squared, right, plus Q squared, okay, using these two equations 12 and 13, you can basically derive the equation that will represent what is the maximum rotor heating limit of the generator. Okay, so how I get these two equations? I basically square P and Q. So square P squared, that will give you this equation here. So it's squaring equation 12, and Q squared, I'm squaring equation 13, and it's giving you the two long expressions here, right? And if P squared plus Q squared, we're adding those two parts together, right? So I've added them here, and I've factorized one common part, which is E naught E of XS to the square, so those two components. And sine squared delta plus cos squared delta can be presented as 1 using your trigonometric identity, and you end up with the two terms that are left there. So in the next step, so I've basically replaced this by 1, right? And I've basically shifted this term in the middle, and I moved this one onto here, right, onto the right. So from equation 13, which we derived earlier, we know that E naught cos delta over XS is equal to Q plus E squared over XS, right? So that one we've derived earlier. And when we look at p squared plus q squared, right, we see that it's got three terms. It's got 1, 2, and 3 terms, right? And we can expand the middle term. Okay, so that's what I've done here. I've expanded it, and from there I can basically write p plus q squared to be equal to this first term, which is here, and I've basically combined those two here. I've written it as 2 minus 2q over e squared minus xs minus of this e squared of xs to the power to the squared, right? So if you rearrange now, you can see that we can shift those two terms on the left-hand side, right? So that becomes p squared of q squared, and those two terms, I've added them on the left-hand side, and I've kept this term on the right-hand side. So this part, which is in blue, can be written in a compact form, which is basically here. So that's q plus e squared over xs, right, to the squared, right? And that basically ends up to the equation of a circle, right? That's equation 14, which basically telling you that it's a circle with coordinate, the coordinate of the circle, right? So you'll see that the x coordinate is 0, but the q coordinate is minus e squared over xs, and the radius of this circle is e naught times e over xs, right? So this is what I've shown in this curve here. This is the coordinate of your circle, which is shown by the green portion, right? This is called the field heating limit of the generator, and it's basically showing you what is the maximum amount of reactive power your generator can produce, right? So as you can see, when you're moving into this region here, you can't exceed this curve. So there is an intersection here between this curve and the green one and the blue one, right? So you have to operate the generator in this section. That's the safe operating point. If you come out, you're going to overheat the armature on this side. And here, if you come out of the green part here, you're going to basically overheat the rotor field winding, right? The intersection here is called the machine rating. So that's basically telling you the rated values for your current in the machine. All right. So this was the derivation of that basically curve that we have shown in this section, which is basically is called the capability curve of the generator. Just take note that this all the derivation and this curve is basically for the power per phase, right? So when we're saying E times I is the apparent power per phase, and we all these variables are basically per phase also. So if you want to convert to a 3-phase, what will happen is you multiply all the parameters by 3, right? So this will become 3 times E naught over xs. This will become 3 times EI, and this will become minus Z over xs. Then you will have what we call a 3-phase capability curve, as opposed to a capability curve which is per phase. All right. Okay, so I will end the lecture for here today, because we've basically completed the entire section on the synchronous generator side. So I'll meet you guys on Friday, and we will basically start with the examples, and we have 2 sections, examples and tutorial, that we will basically cover on Friday, and then next week and we will start getting you ready for your first test one, which will come, I think, in week 5. All right. Thank you, guys.